All right, what's up, everybody? So, this video is an introduction to the standard error of the mean. Now, in the previous video, I introduced you to the idea of the standard error of the mean, and I was comparing it or trying to draw a parallel between the standard error of the mean and standard deviation. Up until this point in the semester, we've been working with, frequency distributions and probability distributions, and we've been describing this idea of standard deviation as the average distance of a singular score. I'm recalling that one of the first examples that we had of this was in the context of describing my I'm pretty sure this was the example of the idea of a mud run, right? How fast I ran the mud run versus other people running that same mud run, and gathering up all this data, determining an average time for the mud run, and then being able to calculate our way down to a standard deviation where we were able to determine where each score, my run time versus someone else's run time, where it exists in relation to the mean with the standard deviation, right? The average distance that each individual score falls from the mean. Now, within this context of samples and populations, as a reminder, we're moving away from talking about individual scores and instead describing how the standard error of the mean is a reflection of how a sample mean deviates or falls away from the expected value or the population mean. Okay, so picking up at that point, standard error of the mean. So when it comes to conducting research, in the last video, I introduced you all to this idea of us collectively as a classroom collecting samples of social media usage data from students, right? So each of us, myself, and then you and your peers, we all surveyed 200 students per person. I surveyed 200, you surveyed 200, and then we were able to determine an average based on each of the samples, right? My 200 students had one average, your 200 students had another average, so on and so forth. While that example is great for illustrating the idea of developing a sampling distribution of the means, where it kind of doesn't quite necessarily meet the expectations of true research, because in reality researchers are rarely drawing more than one or two samples. It's cool in theory to talk about me surveying 200 students, you surveying 200 students, and so on and so forth. But think of the time that it takes to do that, the financial requirement of doing something like that. It's not really feasible to continually collect sample data. As great as that could possibly be, it's just not it's not realistic. So while we cannot necessarily gather population level data, and we don't necessarily collect more than one, maybe two samples of data, the standard deviation of a theoretical sample, a sampling distribution, can actually be determined. And the way that we do that is through this idea of the standard error of the mean. And so, in order to calculate the standard error of the mean, we are going to divide population standard deviation by the square root of the sample size. So that's the formula in text form. Of course, I want to make sure I give it to you in its notation form as well. And so here we have the notation for the standard error of the mean. I'm going to highlight some things as we're moving through this. As a reminder, this symbol here, we have our standard deviation, and then this is our X bar. And so when you combine these two, that is the notation for standard error of the mean. This symbol here should be familiar. We already identified it here, but this is the standard deviation, sigma, and then we have divided by the square root of n. Okay. All right. So we'll kind of plug in some numbers just to see how this ends up, ultimately calculating. So let's say an IQ test population mean is 100, okay, 100 points. I like to use IQ tests just because it's something that we tend to be, collectively familiar with. I won't go into too much detail, but there's actually a really problematic history behind IQ tests, and they're actually not very good at determining what we think they're supposed to determine. But I digress. Let's just kind of focus on the mathematical component of this. So let's say the IQ test, population mean is 100 points, and the population standard deviation is 15. Okay, 15 points is its standard deviation. Let's also say that our sample size of n is 10. Okay. So if we plug in the information that we're pulling, we have the mean of 100, we have a standard deviation of 15, we have a sample size of 10. We'll just kind of plug these into the formula. So we have 15, our standard deviation, divided by the square root of 10. And that ultimately ends up, if you plug the square root of 10 into your calculator, you should get 3.1623, which then you divide 15 by 3.1623, and you may get a number larger than 4.74. There might be a couple other numbers after the decimal, but the final reporting number that we give is going to be 2 decimals. So finding the probability of obtaining any sample mean. So because the sampling distribution takes on the form of the normal curve, as we discussed when talking about characteristics of the sampling distribution of means, we are able to use z-scores and the unit normal table to get the probability of obtaining any sample mean. And this is because z-scores and the unit normal table are based on probability and probability theory. Okay, so this formula here should look very similar, of course, to our z-score formula, but we've made some modifications in order to account for us, instead of working with an individual set of scores, a representation that we are now working with sample means. And so in this case, we have x bar, which is our sample mean, minus the population mean divided by the standard error of the mean. Okay, on the previous slide, we did see the formula for calculating standard error of the mean. So I just want to highlight that, these are things that we are becoming more familiar with. We've been introduced to these things by now. Okay. All right. So the distinction between the standard deviation and standard error of the mean. So standard deviation describes the distances of a set of scores around their mean. A standard error, on the other hand, uses the mean of means, so the expected value, to estimate the difference of population mean from its true mean. Okay. So what affects the standard error of the mean? What are some of the components of the standard error that are going to influence that final number that we calculate through that standard error formula? So based on the formula, we can see that the magnitude, which is the value of the standard error of the mean, is dependent on 2 factors. Okay, if we're looking at the formula, the 2 factors here, one of them is going to be your standard deviation, right? That number, whatever number that is going to influence the outcome that we ultimately determine for the standard error of the mean. What will also determine the value or the magnitude of the standard error of the mean is going to be our sample size. All right. So the variability of scores within the population, which is what the standard deviation represents, and the sample size. Both of these things are going to influence the magnitude or the size of the standard error. So the more similar the population is, so when we remember, this is kind of a callback to measures of variability where we're introduced to variance and standard deviation. Remember that when you have a larger variance and therefore a larger standard deviation, your scores are far more spread out. If you have a smaller variance and therefore smaller standard deviation, your scores are much more likely to be closer together. So the more similar the population is, so the more similar the scores are to one another, and the larger the sample size, the more reliably we can estimate the population mean from sample data. Okay. All right. So we'll pause here.